There is a moon orbiting Saturn that rains liquid methane onto dunes made of frozen smoke. There is another, smaller and closer, that shoots plumes of water 80 times higher than Mount Everest is tall, straight out into the vacuum of space, where the spray freezes into new rings before it ever touches ground again. There is a moon that glows faintly orange in visible light. Its skin stretched and torn by the gravity of the planet, it circles so closely that day and night barely last more than a few hours. And there is a moon, if you can even call it that, following Earth through space right now, so small and so strange in its path that it took astronomers years to agree on what to name the category it belongs to. We tend to think of moons as simple things, a single gray rock hanging in a black sky, reflecting a little borrowed light. That idea comes from looking up at one moon, our moon, night after night, for as long as our species has had eyes to look with. But that familiar shape in the sky is not the rule. It is closer to the exception. Across our solar system alone, more than 250 moons have been confirmed, and new ones are still being found, faint smudges of light discovered years after the fact in old telescope data, or tiny points that wink into visibility only when a spacecraft passes close enough to notice them. Some of these moons are ancient siblings of their planets, born from the same swirling disk of dust and gas. Others are strangers, wanderers captured centuries or eons ago by a gravity they were never born into, still drifting on orbits that betray their foreign origin. Some moons are locked in place, forever showing one face to their planet the way our moon shows one face to us. Others tumble chaotically, never settling into any rhythm at all. Some moons shepherd the very rings they orbit within, carving gaps in ice and dust with nothing but the quiet, patient pull of their own mass. Some might have oceans warmer than anything on the surface of Mars, sealed away under miles of ice, in permanent darkness, for billions of years. Tonight, we are going to drift through all of them. Not as a list, not as trivia, but as a slow unfolding of one idea, that the word moon does not describe one kind of object. It describes a family, vast and strange, bound together only by the fact that each one has surrendered its own path around the sun, in exchange for a tighter orbit around something larger. Everything else about them, their shape, their history, their fate, is its own story. Let the moon over your shoulder, if there is one tonight, be the door you walk through. On the other side of that familiar gray light is a universe of moons, unlike anything you have been taught to picture. Some are dead, some, astonishingly, might not be. We begin close to home, and then we go outward and downward and backward in time, until the very definition of the word moon starts to bend. The moon, you know, begin with the one you already carry in your memory, the one that has hung in Earth's sky for every night of every life that has ever been lived on this planet. Our moon is, in almost every sense, unusual. It is disproportionately large compared to the planet it orbits, more than a quarter of Earth's diameter, a ratio matched by almost no other planet and moon pair in the solar system. Pluto and Charon come close, but Pluto is not what astronomers now call a major planet, so among the 8, Earth and its moon stand nearly alone in that kind of near partnership. The leading explanation for how it formed is called the giant impact hypothesis. Roughly 4.5 billion years ago, when the solar system was still a chaotic nursery of half-formed worlds, a body about the size of Mars, which researchers have informally named Theia, is thought to have struck the young Earth at a glancing angle. The collision would have been violent beyond anything in human experience, vaporizing rock, throwing a ring of debris into orbit around the wounded, molten Earth. From that ring, over a surprisingly short span of time, perhaps only a few hundred years, the Moon is believed to have coalesced. If you had been there, and of course nothing that could have watched was there, the sky above the newly formed Earth would have held a moon so close it filled a vast portion of the horizon, far larger than the moon appears now, glowing faintly red with its own residual heat. Over billions of years, tidal forces between the two worlds have slowly pushed the moon outward at a rate of about 4 centimeters a year, roughly the speed at which a fingernail grows. It is still receding today, and in the far future, billions of years from now, the moon will be too distant and too small in the sky to fully cover the sun during a total eclipse. This slow outward drift is only possible because of something called tidal locking, and understanding it here will make the rest of tonight's journey make sense. Earth's gravity pulls harder on the near side of the moon than the far side, because the near side is simply closer. That slight difference in pull creates a stretching force, a tidal bulge, and over enormous stretches of time, that bulge acts almost like a brake, slowing the moon's rotation until it matches its orbital period exactly. The moon takes about 27 days to circle the Earth, and it also takes about 27 days to complete one full spin on its own axis. The result is that we only ever see one hemisphere, the near side, from Earth. The far side, sometimes mistakenly called the dark side, even though it receives just as much sunlight, remained completely unseen by human eyes until 1959, when a Soviet spacecraft called Luna 3 sent back the first photographs of it. This near side is dominated by dark, flat plains called Maria, a Latin word meaning seas, even though no liquid water has ever pooled there. These are ancient lava flows, solidified more than 3 billion years ago, filling enormous impact basins that were themselves carved out by asteroid strikes, even earlier in the moon's violent youth. The far side, by contrast, is almost entirely mountainous highlands, heavily cratered, with barely any of the dark lava plains at all. The asymmetry between the two hemispheres is still not fully explained, though the leading idea involves differences in crust thickness caused by that ancient giant impact, or perhaps heat from the young, still molten Earth cooking one side of the newborn moon differently than the other. Apollo astronauts walked on this surface between 1969 and 1972, the only humans in history to have stood on another celestial body. They brought back over 300 kilograms of lunar rock and dust, samples that are still being studied today, more than half a century later, revealing details about the solar system's early violence that no telescope could ever show. In the coming years, new missions, including NASA's Artemis program, aim to return humans to that same gray surface, this time with the goal not just of visiting, but of staying. Our moon is airless, waterless in any liquid sense, and geologically almost silent now, its volcanic heart long since cooled. But it set the pattern for everything else we are about to explore. It taught us what tidal locking looks like. It taught us that moons can be scarred battlefields of ancient collisions. And it is, in cosmic terms, one of the plainest, most ordinary moons we will encounter tonight. Nearly everything from here gets stranger. Worlds locked in silence. Tidal locking is not something that happened only to our moon. It is, in fact, the default fate for almost any moon that orbits closely enough to its planet for long enough. Given enough time, measured in the hundreds of millions or billions of years, the tidal forces between a planet and its moon will almost always synchronize the moon's rotation to its orbit. This is why the vast majority of large moons in our solar system, including every major moon of Jupiter and Saturn, show only one face to their planet forever. Picture what this actually means if you were standing on the surface of one of these moons. On Ganymede, the largest moon in the solar system, larger even than the planet Mercury, Jupiter would hang in exactly the same spot in the sky for your entire life, and for the entire life of anyone who ever stood on that spot before you, and anyone who ever will again. It would never rise. It would never set. It would simply be there, a fixed, enormous presence, swelling and shrinking slightly as Ganymede's orbit brought it closer and farther, but never moving across the sky the way our moon moves across Earth's. Now, imagine standing on the opposite hemisphere of that same moon, the side facing away from Jupiter. From there, you would never see the planet at all, not once. An entire hemisphere of that world lives its whole existence with no idea, visually, that a giant planet is the reason it exists on that orbit at all. This near-side, far-side asymmetry is a defining feature of tidally locked moons throughout the solar system, and it often shapes the moon's geology directly because the near side experiences the strongest tidal stresses. Europa, one of Jupiter's 4 largest moons, shows this beautifully. Its icy surface is covered in long reddish-brown cracks called lineae, some of them thousands of kilometers long, and their patterns are consistent with stress caused by Jupiter's tidal pull, working the ice like a hand slowly bending a sheet of metal until it cracks. The cracks on the near side, facing Jupiter, tend to differ in orientation and frequency from those on the trailing side, a fingerprint of the planet's gravitational grip. Tidal locking also produces something less obvious but just as important: tidal heating. As a moon's orbit flexes, even slightly, because of gravitational tugging from the planet or from other moons nearby, friction builds up inside the moon's interior, generating heat the same way repeatedly bending a metal paperclip generates warmth at the bend point. This single mechanism, tidal heating from an eccentric tugged orbit, is the reason several of the moons we will meet tonight are not the dead, frozen rocks you might expect an object so far from the sun to be. It is the reason some of them have oceans. It is the reason at least one of them is the most volcanically active body in the entire solar system, more active even than Earth. Not every moon is tidally locked, though. Very distant, very small, or very recently captured moons often are not, at least not yet, or not in any simple way. Some tumble chaotically, their rotation never settling because their shape is too irregular, or because the gravitational tugging from multiple sources, a planet and its other moons, pulls them in competing directions. Saturn's moon Hyperion is the best known example, a battered, sponge-like object that rotates unpredictably, never repeating the same face to Saturn twice in a fully regular way. If you lived on Hyperion, the very concept of a fixed sky would not exist. There would be no near side and far side. There would only be constant, slow, disorienting change. So already, within the idea of tidal locking alone, we find two extremes. On one end, moons so gravitationally disciplined that their entire surface geology is shaped by a permanent relationship with one hemisphere always facing home. On the other end, moons so chaotic that they never settle at all, tumbling through the dark on orbits that resist any final permanent orientation. Between those two extremes lies almost every moon we know, and it is time now to go looking for water, because some of these locked ancient worlds are not as dead as their icy surfaces suggest. Oceans beneath the ice. If someone told you a generation ago that the largest reservoirs of liquid water in the solar system are not on Earth, you would have had good reason to be skeptical. And yet, that is very likely true. Sealed beneath the frozen crusts of several moons in the outer solar system, astronomers now believe there are oceans of liquid water, kept warm not by sunlight, which barely reaches these worlds at all, but by the same tidal heating that gives some moons their volcanic hearts. Europa is the clearest example. Its surface is a shell of water ice, cracked and shifted, and beneath that shell, evidence gathered from the Galileo spacecraft in the 1990s and from more recent Hubble and James Webb observations strongly suggests a global ocean, one that may contain more than twice the volume of all of Earth's oceans combined, despite Europa itself being smaller than our own moon. That ocean is thought to be sandwiched between the icy crust above and a rocky, possibly volcanically active seafloor below, kept liquid by heat generated as Jupiter's gravity flexes the moon's interior with every orbit. Picture that ocean for a moment. No sunlight has touched it, likely for billions of years. It sits in complete darkness under a roof of ice that may be anywhere from a few kilometers to several tens of kilometers thick, depending on location. If there is life there, and this is very much an open question rather than a settled fact, it would have to survive entirely on chemical energy, the same kind of energy that fuels ecosystems around hydrothermal vents deep in Earth's own oceans, in places where sunlight has never reached either. NASA's Europa Clipper mission, launched in October 2024, is now traveling toward Jupiter's system specifically to study this moon's ice shell and ocean in greater detail, with an arrival expected in the early 2030s. Enceladus, a much smaller moon of Saturn, offers something even more direct, physical proof sprayed straight into space. In 2005, the Cassini spacecraft detected plumes of water vapor and ice particles erupting from cracks near the moon's south pole, nicknamed the Tiger Stripes for their parallel dark appearance against the icy surface. Cassini eventually flew directly through these plumes, sampling their composition, and found not just water, but salts, silica particles consistent with hydrothermal activity, and organic molecules, the carbon-based building blocks associated with, though certainly not proof of, biological processes. Those plumes are the visible signature of a subsurface ocean beneath Enceladus's icy south pole, and ocean scientists now believe may be in direct contact with a warm, rocky core, much like Earth's own seafloor hydrothermal systems. Some of that plume material escapes Enceladus's weak gravity entirely and goes on to form Saturn's E-ring, meaning that if you have ever seen a photograph of Saturn's rings, you have, in a sense, seen a frozen mist of that hidden ocean, flung out into space and caught in perpetual orbit. Consider the scale of what that means. An ocean sealed under ice on a moon barely 500 kilometers across, smaller than the state of Arizona, is venting its contents into space with enough force to be visible from Earth-based telescopes and to physically build a ring around its planet. If you stood at the South Pole of Enceladus in a spacesuit built to withstand temperatures far colder than anywhere on Earth has ever recorded, you would watch geysers taller than the highest mountains on the moon itself, rising in near silence because there is no atmosphere to carry the sound. Water and ice crystals catch in the distant thin light of the sun before falling back down or drifting off into the dark forever. Other moons show hints of similar hidden oceans. Ganymede, the tidally locked giant we met earlier, likely harbors a deep ocean of its own, sandwiched not just under ice but potentially between multiple layers of ice in different phases, some so compressed by pressure that they behave more like rock than what we would recognize as ice on Earth. Callisto, another of Jupiter's large moons, shows similar hints. Even Triton, Neptune's large captured moon, which we will return to shortly, may hide liquid water beneath its strange cantaloupe-textured crust. What ties all of these ocean worlds together is the quiet realization that liquid water, the substance we still consider the single most important ingredient for life as we understand it, does not require sunlight or a comfortable distance from a star. It requires only heat, and heat can come from tides just as easily as it comes from starlight. That single fact has quietly rewritten how many worlds astronomers now consider potentially habitable. And most of those newly considered worlds are not planets at all. They are moons, fire in the dark. Not every moon in the outer solar system hides its heat beneath an icy shell. Some wear it on the surface, openly, violently, continuously. The best example, and one of the strangest objects anywhere in the solar system, is Io, the innermost of Jupiter's 4 large moons. Io is, by every measurement astronomers have taken, the most volcanically active body known anywhere. More active than Earth, more active than Venus, more active than anything else we have ever observed. Its surface is in a state of constant repainting. Sulfur and sulfur dioxide, ejected from volcanic vents, coat the moon in a shifting palette of yellows, oranges, reds, and blacks, a color scheme so distinctive that early photographs sent back by the Voyager spacecraft in 1979 were initially compared, only half-jokingly, to a pizza. The engine driving all of this is, once again, tidal heating. But on Io, the effect is extreme. Io is caught in what is called an orbital resonance with 2 other Jovian moons, Europa and Ganymede. For every orbit Ganymede completes, Europa completes 2, and Io completes 4. This precise mathematical relationship means the moons repeatedly line up in the same configurations, and each time they do, their combined gravity tugs at Io's orbit, preventing it from ever settling into a perfectly smooth circle. Io's orbit stays slightly eccentric, slightly egg-shaped, forever, and that means Io's interior is forever being flexed, squeezed, and released, squeezed and released, generating enormous internal heat through friction, in exactly the way that repeatedly flexing a rubber ball generates warmth inside it. The result is a moon whose surface holds hundreds of active volcanoes, some ejecting plumes of material more than 400 kilometers above the surface, 400 kilometers being roughly the same as the distance from New York City to Washington, D.C., except that plume is launched straight up into space in complete vacuum under gravity so weak that material can travel that far before falling back down. Lava lakes on Io, at a location called Loki Patera, are the largest known volcanic feature of their kind anywhere in the solar system, larger than many of Earth's biggest cities. If you could stand on Io's surface, and no human ever will, given radiation levels from Jupiter's magnetic field so intense they would be fatal within hours, you would find a landscape utterly unlike anything on Earth. There is no liquid water anywhere. Frost patches are made of sulfur dioxide, not ice. Mountains rise not from plate tectonics as they do on Earth, but from a kind of continuous crustal buckling as material is deposited on the surface faster than it can settle. The sky above would be black even at noon, since Io has essentially no atmosphere to scatter light, and Jupiter itself would loom enormous, striped and silent, close enough to be genuinely intimidating in a way that is difficult to convey through description alone. Io is not the only volcanically active moon we know of, though it remains the most extreme example by far. Triton, orbiting Neptune, shows evidence of geologically recent and possibly ongoing cryovolcanism, meaning eruptions not of molten rock, but of extremely cold liquids or slush, likely nitrogen, methane, or ammonia mixed with water, breaking through Triton's frozen crust. Voyager 2 photographed active plumes on Triton's surface in 1989, rising several kilometers before drifting sideways under the influence of thin, high-altitude winds. A genuinely bizarre sight. Eruptions of frozen material producing something that behaves in that fleeting moment almost like weather. Even Enceladus, whose watery plumes we explored a moment ago, can be understood as a cryovolcanic moon, its geysers a colder cousin of Io's molten fountains, and some of Uranus's smaller moons, along with Pluto's large moon Charon, show surface features that hint at cryovolcanic activity sometime in their past, even if nothing is actively erupting there today. What Io teaches us, more clearly than any other moon, is that distance from the Sun is nearly irrelevant to a world's internal energy. Io receives roughly 25 times less sunlight than Earth does, and yet it is, geologically speaking, one of the most energetic places we know of anywhere. The heat comes from below, from gravity itself, squeezed out of orbital mathematics and turned into fire. It is a reminder that a moon story is written far more by its relationship to its planet and its neighboring moons than by its relationship to any star. The captured ones, so far, every moon we have visited was born in place or something close to it, coalescing from the same disk of material that formed its planet, a child of the same cosmic event. But not all moons share this origin. Some are strangers. Some began their existence somewhere else entirely, on independent orbits around the Sun, and were only later pulled into permanent orbit around a planet they never should have belonged to. Mars offers the clearest, closest example. Its two moons, Phobos and Deimos, are small, lumpy, irregularly shaped objects, nothing like the round, differentiated bodies formed through gradual accretion. Phobos, the larger of the two, is only about 22 kilometers across at its widest point, smaller than many cities on Earth. For decades, the leading theory held that both moons were captured asteroids, wanderers from the nearby asteroid belt that strayed too close to Mars and were caught by its gravity, unable to escape again. More recent analysis has complicated that story. The orbits of Phobos and Deimos are unusually circular and lie almost exactly in Mars's equatorial plane, which is difficult to explain through simple capture, since captured objects typically settle into more elongated, tilted orbits, at least at first. This has led some researchers to propose an alternative, that both moons formed from debris thrown into orbit after a massive impact on Mars itself, not unlike the giant impact hypothesis for our own moon, just on a much smaller scale. The debate is not fully settled, and Japan's Martian Moons exploration mission, planned for launch in the mid-2020s with sample return expected by the early 2030s, aims to bring back physical material from Phobos that should finally answer the question directly by revealing the moon's true chemical fingerprint. Whatever their exact origin, Phobos and Deimos share a common fate with all small, close-orbiting moons. They will not last forever, at least not in their current arrangement. Phobos orbits so close to Mars, only about 6,000 kilometers above the surface, closer relatively than any other known moon orbits its planet, that tidal forces are very slowly pulling it inward at a rate of about 2 centimeters per year. In perhaps 30 to 50 million years, astronomers expect Phobos will either be torn apart by Mars's gravity, forming a temporary ring, or will spiral down and crash into the planet's surface entirely. It is one of the very few moons in the solar system with a known, calculable expiration date. Farther out, Neptune's large moon Triton tells an even stranger capture story, one written directly into the geometry of its orbit. Triton orbits Neptune backward, retrograde, meaning it travels in the opposite direction to Neptune's own rotation, and its orbit is also tilted at a steep angle relative to Neptune's equator. No moon that formed naturally alongside its planet would ever end up on an orbit like this. The overwhelming evidence points to Triton having originated in the Kuiper Belt, the same distant icy region of the solar system where Pluto resides, as an independent dwarf planet in its own right, before being gravitationally captured by Neptune, likely billions of years ago in an encounter that also may have violently ejected some of Neptune's original natural moons. Triton's capture explains a great deal about the moon's unusual character. Since being caught, its orbit has been gradually circularized by tidal forces, and in that process, enormous amounts of tidal heating would have been generated, likely explaining Triton's youthful-looking, sparsely cratered surface, and quite possibly its cryovolcanic activity as well, that strange cold volcanism we explored a moment ago. In an almost poetic irony, Triton's fate now mirrors Phobos's on a much longer timescale. Because its orbit is also gradually decaying due to tidal forces, astronomers estimate that in 3.5 billion years or so, Triton, too, will eventually be torn apart by Neptune's gravity or spiral down onto the planet, ending its long captivity the same way it may have ended its independence. Jupiter and Saturn host dozens of small, irregular, distant moons that are almost certainly captured objects as well. Tiny bodies just a few kilometers across, orbiting on wildly tilted, eccentric, sometimes even retrograde paths far from their planets, in orbits that would never arise naturally. Many of these were only discovered in the last 2 decades through patient, wide-field telescope surveys, and they likely represent asteroids or even fragments of larger captured bodies that broke apart after arriving. Capture, then, is not a rare event in the story of moons. It is one of at least two fundamentally different ways a world can end up locked to a planet that never gave birth to it. Some moons are children of their planet. Others are guests, caught and held, sometimes for billions of years, sometimes only until gravity finally finishes the job of pulling them apart. Shepherds of the rings. If capture explains how strangers become moons, there is another category entirely. Moons whose entire identity is defined not by their own composition or history, but by their role in shaping something else. These are the shepherd moons, small bodies embedded within or orbiting just alongside planetary ring systems, and their gravity is the invisible sculptor keeping those rings organized. Saturn's rings offer the finest examples anywhere in the solar system. The rings themselves are made of countless individual particles of ice and rock, ranging from grains smaller than sand up to chunks the size of a house, all orbiting Saturn in a flat, thin disk that, despite spanning hundreds of thousands of kilometers across, is in most places only about 10 meters thick, proportionally thinner than a sheet of paper compared to its width. Left alone, gravitational interactions between all these particles would tend to smear the rings into a smoother, less structured shape over time. But Saturn's rings are not smooth. They are divided into distinct bands with sharp edges, narrow gaps, and delicate braided structures, and shepherd moons are the reason. Two small moons, Pan and Daphnis, orbit directly within gaps in Saturn's rings, gaps that exist specifically because these moons have gravitationally cleared them out. Pan, roughly 35 kilometers across, orbits inside the Inky Gap, a 250-kilometer wide clearing in the outer A ring. As Pan moves through this space, its gravity nudges nearby ring particles, some inward, some outward, maintaining the gap's edges with remarkable precision and even carving delicate wave patterns into the ring material on either side. A bit like a boat leaving a wake as it moves through still water, except the wake here is frozen into a permanent orbiting pattern of ice. Daphnis performs a similar role in the narrower Keeler Gap, and because Daphnis has a slightly tilted inclined orbit, it pulls the edges of the gap up and down as it passes, creating vertical waves in the ring material, structures that rise kilometers above the otherwise razor-thin ring plane, visible in detailed images from the Cassini spacecraft as strange, feathery disturbances that seem almost alive in their movement, even though the entire pattern is nothing but the predictable result of gravity acting on ice over and over again. Two other small moons, Prometheus and Pandora, orbit just outside the narrow, ropey F ring, one slightly closer to Saturn, one slightly farther. Their combined gravitational influence, tugging the F ring's particles in opposing directions as the moons pass by on their slightly different orbits, is thought to be responsible for the ring's unusually narrow, twisted, and clumpy appearance, unlike any of Saturn's broader, smoother rings. Prometheus, in particular, has been observed periodically dipping close enough to the F ring to pull streamers of material directly out of it, like a finger dragging through a curtain of gauze, leaving faint, dark channels that persist for a time before slowly fading. The physics behind all of this is not exotic. It is simply gravity, operating patiently over immense stretches of time. At a scale where even a moon only 30 kilometers across, far too small to ever hold on to an atmosphere or host any kind of geological activity of its own, can still leave a permanent, visible signature on a ring system spanning hundreds of thousands of kilometers. There is something worth sitting with in that fact. These shepherd moons will likely never be visited by any spacecraft up close again for years. They are too small and too faint to draw much individual attention. And yet each one is, in its own quiet way, an active sculptor, continuously working, continuously shaping the appearance of one of the most photographed objects in the entire solar system. Every image of Saturn's rings that has ever captured your attention, every gap, every narrow braided strand, is in part a portrait of these small, unglamorous moons doing the only thing they do, pulling gently forever on the ice around them. Trojans and traveling companions. Beyond the shepherds lies a stranger category still, moons that do not orbit alone but share their orbital path with another moon entirely, locked together not by touching or colliding, but by a delicate gravitational balancing act first described mathematically by the 18th century mathematician Joseph Louis Lagrange. Lagrange discovered that within any system of two large bodies orbiting each other, such as a planet and a moon, there exist 5 specific points in space where a much smaller third object can sit in stable, or at least semi-stable, gravitational equilibrium, held in place by the combined pull of both larger bodies along with its own orbital motion. 2 of these points, known as the leading and trailing Lagrange points, sit exactly 60 degrees ahead of and 60 degrees behind the larger moon, along the same orbital path around the planet. Objects trapped at these points are called Trojans, a name borrowed from the Trojan asteroids that share Jupiter's orbit around the Sun in exactly this same configuration. Saturn provides the finest known examples of Trojan moons. Tethys, one of Saturn's mid-sized icy moons, has 2 much smaller Trojan companions named Telesto and Calypso, sitting at its leading and trailing Lagrange points respectively. Both are small, elongated, heavily cratered bodies, only a few tens of kilometers across, and both have remained locked in this 3-body dance with Tethys for what appears to be a very long time, their positions gently oscillating around the exact Lagrange points rather than sitting perfectly still, in slow, looping paths that never quite settle, but also never escape. Dione, another of Saturn's moons, has a similar arrangement with 2 Trojan companions of its own, Helene and Polydeuces. Helene, the larger of the 2, is potato-shaped and heavily cratered, and its stable position 60 degrees ahead of Dione has likely persisted since not long after the Saturn system itself finished forming, meaning these small moons may have been locked into their strange borrowed orbits for something close to 4 billion years. Picture what this configuration would look like if you were standing on Tethys, watching the sky. Telesto and Calypso would not appear as ordinary moons rising and setting in the way our moon does over Earth. Instead, they would seem to hover, drifting only slowly relative to the horizon, forever holding roughly the same relative position in the sky, night after night, year after year, for as long as the arrangement holds. It is a kind of orbital choreography with no true parallel on Earth. 3 bodies moving together through space, 2 of them tiny and dependent, one of them large and, in a strange sense, unaware that it is being escorted. This Trojan relationship is delicate, though. It depends on precise mass ratios between the bodies involved and on the absence of significant outside disturbance. Too much gravitational interference from other moons, and a Trojan configuration can become unstable over long timescales, with the smaller body eventually drifting away from its Lagrange point entirely, either escaping into an independent orbit or, in some computer simulations of similar systems, spiraling inward toward a collision. The fact that Tethys and Dion's Trojan companions have survived for so long suggests the Saturn system, at least in this particular corner of it, has remained remarkably calm and undisturbed since its early chaotic formation settled down. Earth itself has hosted Trojan-like companions in a more informal sense. Tiny asteroids temporarily captured near its own Lagrange points relative to the Sun, though none of Earth's known companions have proven to be as stable or as long-lived as Tethys's and Dion's true moons. Still, the discovery of even temporary Trojan objects near Earth hints that this particular gravitational trick, three bodies locked into cooperative motion, may be more common throughout the universe than the handful of confirmed examples around Saturn would suggest. We simply have not yet developed the observational tools to find most of them, especially around planets outside our own solar system, where individual moons remain, for now, almost entirely undetectable. The quasi-moons. There is one more category, stranger still, and it brings us back to Earth's own sky, to a kind of companion that barely qualifies as a moon at all, and yet cannot quite be dismissed as anything else either. A quasi-satellite is an object that appears, from Earth's perspective, to loop around our planet in a slow, looping, moon-like path, sometimes for decades or even centuries at a stretch, without actually being gravitationally bound to Earth in the way our true moon is. Instead, a quasi-satellite is independently orbiting the Sun, on a path that happens to be extremely similar in size and timing to Earth's own orbit. Because both Earth and the quasi-satellite are moving around the Sun at nearly matching speeds and distances, the object appears, when viewed from Earth, to trace out a slow, curling loop in the sky over the course of each year, a shape that looks remarkably like an orbit around us, even though, from the Sun's perspective, both Earth and the object are simply following their own separate, independent paths that happen to be gently synchronized. The clearest known example is an asteroid called Kamo'oalewa, discovered in 2016 and named after a Hawaiian word evoking an offspring that travels on its own, a fitting choice. Kamo'oalewa is tiny, likely less than 60 meters across, smaller than a football field, and it has been quietly tracing its looping quasi-orbit near Earth for at least a century, possibly for much longer, and current models suggest it may continue in this configuration for centuries more before gravitational nudges from the Sun and planets eventually shift its path away. What makes Kamo'oalewa especially fascinating is a 2021 analysis of its reflected light, which found a composition surprisingly similar to lunar rock, the kind of material found on our own moon's surface. This has led to a genuinely striking hypothesis, still unconfirmed but taken seriously by researchers, that Kamo'oalewa may be a fragment blasted off our own moon by an ancient asteroid impact, flung into an independent solar orbit, only to drift, over millions of years, into this strange, synchronized dance with the very world it once broke away from. If true, it would mean Earth has, in a sense, a fragment of its own moon quietly looping nearby, disguised as an unrelated asteroid, discovered only because of one careful, patient astronomical survey. Earth is not the only planet with known quasi-satellites. Venus has at least one, an asteroid called 2002 VE68, which has occupied its quasi-orbital configuration for at least 7,000 years, according to orbital modeling, and may continue for thousands more. Other quasi-satellites have been identified near Jupiter, Saturn, and Neptune as well. In every case, these objects blur a line that feels, at first, like it should be simple and obvious. Is a moon defined by gravity, by appearance, or by the shape of its path through the sky? Quasi-satellites suggest the answer is more nuanced than any single definition allows. From the ground, looking up, an observer with no access to precise orbital mechanics might reasonably describe Kamo'oalewa's slow, looping motion as moon-like, because from a naive, visual standpoint, it behaves exactly the way a small, distant moon would behave. Only the deeper mathematics, the true gravitational bookkeeping of who is bound to whom, reveals that no true binding exists at all, only a temporary, beautiful coincidence of timing and orbital geometry, one that could, in principle, happen anywhere in the universe where two bodies orbiting a star happen to share nearly the same year. There is something quietly moving about an object like this, drifting near a planet, appearing to belong to it, shaped by nothing but chance and orbital arithmetic into something that looks, for a while, like companionship. It commits to nothing permanently. It simply happens to be nearby on a schedule that will not last forever, and for now, that is enough to make it look, from where we stand, remarkably like a moon. Moons that might have been planets. Step back now and consider a different way of dividing the family of moons, not by how they formed or how they move, but by what they might have become had circumstances been only slightly different. Titan, Saturn's largest moon, is bigger than the planet Mercury. It is the only moon in the solar system known to possess a dense atmosphere, thicker even than Earth's, composed mostly of nitrogen, with a hazy orange tint caused by complex organic molecules formed through chemical reactions high in its upper atmosphere. Beneath that thick air, Titan has lakes and rivers and even seas large enough to be named individually, but they are not filled with water. At Titan's surface temperature, roughly minus 179 degrees Celsius, water is frozen rock hard, forming the mountains and bedrock of the landscape. Instead, Titan's liquid bodies are filled with methane and ethane, hydrocarbons that exist in liquid form at those extreme temperatures, and the moon experiences something genuinely similar to Earth's own water cycle, just built from entirely different chemistry. Methane rain, methane rivers, methane evaporation, methane clouds. The Cassini spacecraft, along with the Huygens probe it released to land directly on Titan's surface in 2005, revealed a strange, weathered landscape shaped by dunes, drainage channels, and shorelines eerily reminiscent of Earth, despite being built from utterly alien materials. If Titan orbited the Sun independently, rather than orbiting Saturn, it would likely be classified without hesitation as a planet in its own right, larger than Mercury, with weather, seasons caused by Saturn's own 29.5-year orbital period, and its own distinct atmosphere and surface chemistry. Its status as a moon, rather than a planet, is purely an accident of gravitational hierarchy, a matter of what it orbits, not what it is. Ganymede tells a similar story. As we mentioned earlier, it is the largest moon in the solar system, larger than Mercury, and it possesses something no other moon is known to have: its own internally generated magnetic field, evidence of a liquid iron core still churning with enough motion to create the same kind of dynamo effect that generates Earth's own protective magnetic field. If Ganymede orbited the Sun independently, it would almost certainly be considered a planet, and a geologically fascinating one, with its likely subsurface ocean and its unique self-generated magnetism setting it apart from every true planet except Earth itself. Then there is Pluto and its largest moon, Charon, which together form perhaps the strangest edge case of all. Charon is so large relative to Pluto, roughly half its diameter, that the two do not orbit in the typical planet-moon arrangement, where a large body sits nearly still while a small one circles it. Instead, Pluto and Charon orbit a shared point in space that lies outside of Pluto itself, called the barycenter, meaning both bodies are, in a real physical sense, orbiting each other, locked together in a mutual dance rather than one clearly dominating the other. Some astronomers have argued that Pluto and Charon should be considered a binary system rather than a planet or dwarf planet and its moon, precisely because the usual hierarchy breaks down so completely in their case. These borderline cases matter because they reveal something important. The categories we use, planet, moon, dwarf planet, are human inventions, useful for organizing our understanding, but the universe itself does not recognize these labels as fundamental. Titan does not know it is technically a moon and not a planet. Ganymede's magnetic field does not care what word we use to describe the object generating it. Nature simply produces bodies of enormous variety in every size, every composition, every kind of orbital relationship, and it is only afterward that we, looking up from Earth, decide which drawer to file each one into. Somewhere out there, orbiting other stars entirely, there are almost certainly moons larger than Earth itself, orbiting gas giants larger than Jupiter, worlds that would be called planets without a second thought if only they orbited their star directly instead of orbiting another planet first. We have not yet confirmed a single exomoon with certainty, though several intriguing candidates have been proposed from Kepler and Hubble data, most notably a controversial candidate called Kepler 1625b1, whose existence remains debated within the astronomical community. But the mathematics governing planet and moon formation gives us little reason to think our solar system's scale of moons represents any kind of upper limit. Larger moons, moon-sized worlds that might themselves be capable of holding oceans, atmospheres, even in principle, the conditions for life, may simply be waiting for our instruments to grow sensitive enough to notice them, tucked into the glare of their parent planets, hidden in data we have already collected but have not yet learned to read closely enough. The moons. We have not yet found everything explored so far comes from direct observation, spacecraft flybys, telescope surveys, physical samples brought back to laboratories on Earth. But the story of moons does not end at the edge of what we have confirmed. It extends into everything we suspect, everything the mathematics allows, and everything we simply have not yet had the technology to see. Exomoons, moons orbiting planets around other stars, remain almost entirely theoretical, not because scientists doubt they exist. Current models of planet formation suggest moons should be an extremely common byproduct of how planetary systems form, but because detecting them is extraordinarily difficult. A moon orbiting a distant exoplanet would need to be detected through subtle secondary effects, tiny additional dips in starlight during a transit, minuscule timing variations in when the planet itself passes in front of its star, effects so small that our current generation of telescopes sit right at the very edge of being able to notice them at all, buried in noise that is difficult to fully rule out. The James Webb Space Telescope, along with future observatories currently in development, is expected to push this boundary further in the coming years, and many astronomers consider the confirmed discovery of the first definite exomoon to be a matter of when, not if. Not when that discovery comes, it will likely reveal something our own solar system has not shown us directly. A genuinely Earth-sized or larger moon orbiting a gas giant within its star's habitable zone, a world where liquid water might exist not on the surface of a planet at all, but on the surface of a moon, warmed both by its star and by tidal heating. From the planet it orbits, doubling its chances of holding on to the conditions life might need. There is also the question of moons that once existed but no longer do. Several of the small, irregular, distantly orbiting moons around Jupiter and Saturn show signs of having once been part of larger bodies that broke apart, either through collisions with other objects or through tidal disruption when their orbits carried them too close to their planet. Some scientists believe Saturn's rings themselves may be, at least in part, the remnants of one or more shattered moons, destroyed sometime in the last few 100 million years, a timescale that is startlingly recent in the context of a solar system 4.5 billion years old. If this theory holds, it means Saturn's rings, one of the most visually iconic sights in the entire solar system, may in a very real sense be a moon's grave, the scattered, glittering remains of something that used to be whole, now spread into a thin, luminous halo that outlives the object it once was. And there are moons still hiding, quietly, in our own solar system, waiting to be found. New, small moons around the giant planets are still being discovered on a fairly regular basis, thanks to increasingly sensitive wide-field surveys capable of picking out faint points of reflected sunlight kilometers across, hundreds of millions of kilometers from Earth. In 2023 alone, dozens of new small moons were confirmed around Saturn, most only a few kilometers wide, pushing Saturn's total known moon count past 145, temporarily overtaking Jupiter as the planet with the most confirmed moons in the solar system, a title that has shifted back and forth in recent years as both planets continue to reveal previously unnoticed companions. It is worth sitting for a moment with the strange humility in that fact. We have sent spacecraft past every planet in our solar system. We have landed probes on multiple moons. We have brought lunar rock back to laboratories on Earth. And yet, we are still discovering new moons, new small, cold, silent worlds, hiding in plain sight, simply because they are faint, and space is unimaginably large, and looking carefully takes time. The space between worlds. Draw back now, far enough to see the whole family we have wandered through tonight. A tidally locked moon showing one eternal face to its planet. An ocean sealed for billions of years beneath a shell of ice, warmed only by the flexing of gravity. A volcanic world painted orange and black by sulfur its heat born entirely from orbital mathematics rather than any star. A captured stranger, foreign-born, doomed eventually to fall or be torn apart. A shepherd sculpting rings with nothing but its own quiet mass. A Trojan holding its position through a delicate three-body balance struck billions of years ago and somehow never broken. A quasi-satellite looping past a planet it doesn't actually belong to, borrowing the appearance of companionship without any of gravity's true commitment. A giant, moon-like only by an accident of orbit, that could easily have been called a planet in any other arrangement. None of these are separate stories, not really. They are variations on a single, quiet theme, repeated across the solar system with almost endless creativity. Something smaller, caught in the gravity of something larger, and the long, patient consequences that follow from that simple relationship, stretched out over billions of years. It is worth remembering, too, how recently most of this understanding arrived. A little over 400 years ago, when Galileo first turned a telescope toward Jupiter in 1610 and saw four small points of light shifting position night after night, the very idea that a planet could have its own moons, its own miniature solar system in orbit around it, was genuinely radical. Evidence used at the time to argue that Earth need not be the unmoving center of everything. Everything we have explored tonight, tidal locking, subsurface oceans, volcanic moons, captured strangers, shepherd moons carving rings, Trojans locked in three-body harmony, quasi-satellites tracing false orbits, has been discovered, confirmed, or in some cases only seriously proposed within the last 60 years, most of it within the lifetime of people alive today. We are living through the earliest chapters of understanding what moons actually are. There may be, across our galaxy alone, more moons than planets, more moons than stars, more moons than any number the human mind is built to hold on to with any real intuition. Around ordinary-looking stars, in systems we have never imagined, there may be moons larger than Earth, warmed just enough by starlight and by tides together to hold liquid water on their surface, or beneath it in the dark. Somewhere, perhaps, one of them is doing exactly what Enceladus does, quietly venting the evidence of a hidden ocean out into space, waiting only for someone or something, distant and patient enough, to notice. You began tonight looking up at a single, familiar moon, if there was one in your sky. It is worth ending the same way. That plain gray light, tidally locked, scarred by ancient impacts, drifting slowly outward by a few centimeters every year, is not a lesser version of anything we explored tonight. It is simply the version we happen to be born beneath. Somewhere else, on some other night, under some other sky, another kind of eye, if one exists, might be looking up at an orange volcanic moon, or a moon veiled in nitrogen haze, or the looping, borrowed path of a quasi-satellite, and calling it quietly home. Let the sky settle now. Let the moon, wherever it sits tonight, simply be what it has always been: close, familiar, and, if you let yourself remember everything it represents, far stranger than it first appears.